Hello and welcome back to the National Solar Observatory. We're getting ever closer to the total solar eclipse, less than 3 months to go now. We hope you found these webcasts a useful tool in preparing for the solar eclipse. We've tried to cover a whole range of different topics, from storms on the sun, all the way through to the Sun-Earth-Moon system and how solar eclipses happen. Today we're going to be bringing it back home and we're going to be focusing on how the sun affects the Earth and how the Earth is dependent on the sun. Of course, there's some very obvious ways in which we're dependent on the sun. The sun is the source of light that allows us to see our surroundings outside. It's the source of heat that allows us to live comfortably. It's the source of our energy that allows plants to grow and our animals to feed. And more recently is the source of solar energy, which allows us to power our electronics, and it helps to contribute to the electric grid. We're extremely fortunate here on Earth that we are located where we are. If we were on Venus or we were on Mars, we wouldn't be able to survive as a human race. We live in what's called the Habitable Zone, and this is a region around a star that is just close enough to get sufficient light and heat, but not so close that we are fried or overexposed. We're not too close, we're not too far away, we're just in the middle where it's just right. This is often called the Goldilocks Effect. And this Goldilocks zone is something that we look for when we're looking for extrasolar planets. But aside from looking at the distance of a planet from a star, there's other factors that we have to remember to take into account. For example, we spoke in earlier webcasts about solar storms, solar flares and coronal mass ejections. If there's a planet that's located in the Goldilocks zone, but the star nearby is producing enormous solar flares at a very high frequency, life most likely won't be able to survive there. So solar activity, or in this case stellar activity, is something that we also have to take into account when looking for extrasolar life. For example, a recently discovered potential Earth-like planet that is orbiting around Proxima Centauri b also has very extreme space weather events. Its local star produces solar flares that are so large that making that Earth 2.0 is really not a viable option. So our dependency on the sun really goes beyond the light and the heat and the things that we need to survive in a positive way. We also have to be aware of some of the challenges of living within the atmosphere of a star. Throughout this webcast series, we've covered some of these ideas already. We've talked about solar storms and coronal mass ejections. Today we're going to be bringing in an expert from NOAA's Space Weather Prediction Center, who is a space weather forecaster, and he's going to tell us what we should be looking for when we're looking for space weather activity in our atmosphere. But before we get into that detail, I want to bring you back to the Earth again for just a moment. So the Earth's atmosphere is made up of multiple layers, and the outermost layer of the atmosphere is called the ionosphere. So in previous webcasts, we've mentioned the word ion. This is an atom whose electrons have been pulled off by excess energy. So the ionosphere is a literal sphere of ions that's on the outside of our atmosphere. But the ionosphere is not quite spherical. Because it's predominantly caused by emissions coming from the sun, it's much denser on the side closest to the sun, and on the side that's far away from the sun, it's much, much thinner. So the ionosphere is almost like an oval-shaped blob that the Earth rotates inside of. Some of the specific effects that we can predict, although we're not entirely sure for certain, that will happen during the solar eclipse are going to happen in this region of the atmosphere. Since this region occurs as a result of emission from the sun ionizing the outer layers of the Earth atmosphere, that would suggest that when the moon moves in front of the sun, it's going to block some of that ionization effect. So there are some theories that predict there will be waves that are launched in the upper atmosphere during the solar eclipse as a result of changes in this density profile. So essentially, you can think of it as being like a dip in the depth of the ionosphere. Changes in the ionosphere are some of the things that we really watch out for with space weather. For example, when we're using long-wave radio communications, the radio waves are bounced off the ionosphere to get all the way around the globe. This is how we can use them for worldwide communication systems. However, if the density and the thickness of the ionosphere changes as a result of excess solar energy, then the location of those radio waves all of a sudden become uncertain. So the ionosphere is affected by significant changes in the sun's output, and predominantly in this case as a result of solar flares. So when we get a solar flare, we talked about it being a sudden release of light and energy, and that light and energy causes extra ionization to occur in the Earth's ionosphere. So it's important for us to understand the source of solar flares and how they propagate and the size of them and where on the sun they are occurring, so as we can be prepared for any effects that might happen here on Earth. Similarly, coronal mass ejections are another aspect of space weather that we have to pay attention to. Coronal mass ejections, or CMEs for short, are large eruptions of magnetic field and plasma, so highly ionized gases. And these eruptions leave the sun, they erupt from the sun and they travel through space. And if they happen to be directed towards the Earth, they can interact with the Earth's magnetic field. So if the magnetic field in the coronal mass ejection is oriented in a particular way, it can interact with the Earth's magnetic field. So the Earth's magnetic field looks like a bar magnet that has been dragged out on one side and squished up on the other side. And it has a direction. So the magnetic field runs between the North Pole and the South Pole. Equally, the coronal mass ejection's magnetic field also has a direction. Now, if they happen to be pointing in the same direction, not much happens. This is a bit like taking the two magnets with the same polarity, so a north and a north, for example, and trying to push them together. They don't really do much. However, if you flip one of them around and you have a south pole and a north pole and you push them together, they're going to try and stick together. Now, if the Earth's magnetic field is pointing one way and the coronal mass ejection's magnetic field is pointing the other way, then as they approach each other, they're going to try and connect or reconnect. And this can cause significant changes in the Earth's magnetosphere. Now, this is nothing to be alarmed. This is actually the reason why we get aurora borealis. So it's actually something that has quite a positive effect. As the Earth's magnetic field gets reconfigured, it gets pushed back towards the night side of the Earth and gets compressed in the inner layers of the magnetic field. This compression causes bursts of energy to be released, which accelerate electrons down the magnetic field lines. And these electrons enter into the Earth's atmosphere at the north and south magnetic poles. As the electrons that are carrying this extra energy approach the north and south poles, they meet this wall of atmosphere. As they hit the atmosphere, the energy that they're carrying gets distributed, it gets released into the atmosphere. And in turn, it excites the atoms that are located in the atmosphere. And those atoms, they release that extra energy by glowing. And that glow is what we see as the aurora. So we see the greens and we see the reds. Sometimes you'll see purple. That's all as a result of emission coming from all the different atoms in the atmosphere. The other piece of space weather that we haven't mentioned much so far is a phenomenon called coronal holes. So far we've talked a lot about solar flares and coronal mass ejections, and these occur in active regions, which are regions of closed magnetic loops. These are areas where the magnetic field pops out through the surface, loops around and goes back into the surface of the sun reasonably close by. Coronal holes are regions where the magnetic field comes out through the surface, but it doesn't return back again. It's connected all the way out through space. So this flow of particles leaving the sun and traveling out into space can also be the source of some of our space weather effects. This is especially interesting if we have a region coming from a coronal hole that interacts with a region from a coronal mass ejection. And where those two things interact with each other or overlap each other, that's when we get some of the really, really exciting and interesting space weather effects. Returning to the natural world, the solar eclipse, of course, will be a wonderful time to observe changes in the behavior of animals. Once totality hits, birds think that it's time to go to sleep and you see them starting to nest down for the night. Nocturnal animals think that it's time to come out and hunt and find food. So observing the natural world around you is also a really great way of experiencing the solar eclipse. The GLOBE program is a great way of participating in large-scale studies of this. You can actually measure the temperature of the atmosphere where you are, whether you're on the path of totality or not, and contribute to this nationwide project that will be investigating changes in the temperature and the darkness levels across the whole nation. So next up, we're going to demonstrate a short activity that really allows you to get into the depth of how dependent we are on the sun and how important it is for our everyday life. This activity comes from the Night Sky Network and was created by the Astronomical Society of the Pacific. It's a great way of having people really think critically about the source of their energy. Where does their electricity come from? Where does their food come from? I find this to be particularly interesting when working with young adults and teenagers, people who may not yet be attuned to where the power for their cell phones come from, for example. Electricity doesn't just magically arrive in a wall outlet, it has to be generated from somewhere. So this activity begins with every participant receiving a card. So on the front of every card, there is a picture and a description word, and on the back of every card, there is a short explanation of that particular item. This card, for example, reads, "Corn. Through the process of photosynthesis, I convert energy from the sun into energy stored in my cells." So the goal of this game is that every participant has one of these cards and uses them to find their source of energy. So everybody receives one of these, holding them high above their heads so as everybody can see the pictures and the descriptors on them, and moves around and speaks with everybody else in the group, trying to identify their source of energy. So in this case, somebody having the cereal card would be seeking out the corn. So the cereal card reads, "I'm a plant-based food. I have stored energy from the plants," and in parentheses, corn, "used to make me." So that means that corn is a source of energy for the cereal. This extends across many different areas, cards that are food related, there's cards that are electricity related, cards that describe how petroleum is produced for automobiles. The idea here is that everybody works as a team to try and find their source of energy, and some of those energies will have multiple offshoots towards the end of their chains. Once everybody has identified what their source of energy is, have everybody arrange themselves so as they fan out away from the sun. The cheat for this is that the sun is the center of all of these energy chains. So putting the sun at the center and allowing all of the energy chains to fan out from the sun will really help to demonstrate this. Have everybody lay their cards down on the floor and have them study the different chains of energy around the entire system. This not only is a great icebreaker activity as it forces people to interact with each other, it also is a great conversation starter. If you're having any kind of conversations about energy or about the sun, renewable energy is another topic that bridges both of these. Depending on your audience, sometimes it's best to allow the audience to lead the discussion. For some, this might just be a reminder of where our energy comes from and helping them to remember to be slightly more conscientious about their energy usage. For others, this might be a whole new piece of information for them, and they may be seeing this for the very first time. Asking questions such as, what do you notice? What surprises you? What were you not expecting? They're good conversation starters. Having people also take note of the length of energy chains can make for some interesting conversation. If you plan to do this activity more than once, we recommend that you try to laminate the cards. This will make sure that they stay clean and robust. If you plan on doing this just the once, perhaps printing these on heavy paper or cardboard would do a good job as well. We do recommend that you print them in large format, as smaller cards will be more difficult to see across a group. But ultimately, this is really just a great game to have fun with and to allow participants to explore. It is important to do some homework in advance if you have less than 30 participants. So the full set of cards is 30 cards. But if you have fewer than 30, you need to make sure that your energy chains will be complete. So make sure that you pick the energy chains that start at the sun and each step is included. You don't want to leave out a critical step and have somebody without an energy source. Next up, we're going in a very different direction, and we have Robert Steenburgh from NOAA's Space Weather Prediction Centre, who's going to tell us what it's like to be a space weather forecaster and what space weather forecasters are looking for and why it's important.
Hello, my name's Rob Steenburgh. I'm a scientist and forecaster here at the Space Weather Prediction Center in Boulder, Colorado. We forecast space weather for a variety of reasons. It started out in the really in the 40s because we used high-frequency radio communications to talk over large parts of the Earth, and we needed to understand what the ionosphere was doing in order to do that effectively. And the ionosphere is influenced by the sun, and so beginning to understand that helped us with propagation. From there, as technologies move forward, our level of technological dependence continues to increase, and space weather has a huge impact on technology, in particular things like satellites and spacecraft, humans in space. all the way down to the ground here on Earth, where you have impacts on the electric power grid, for instance, on aircraft communications, things like that. And all the way to seeing the aurora. A lot of people are interested in being able to see the aurora. So it's a collaboration between research, operations, between government and commercial. So we forecast space weather as a way of alerting different communities of potential impacts to their systems and to making sure people are safe and that we can deal with the impacts so that we're prepared. One piece of information we'd love to know is what that magnetic configuration is as it leaves the sun, and really being able to watch it evolve as it moves towards Earth, because that's the determining piece, one of the determining pieces of the strength of the magnetic storm. It's a key piece of information. We don't have that until the thing's at our doorstep. So on the sun, we look for the sunspots. The sunspots that grow, become more complex and big, typically produce flares. So the flares are here in 8 minutes, affecting our ionosphere. You see a degradation of HF communications on the sunlit side of the Earth. Sometimes those flares can also produce energetic particles, proton events. So you can see those arrive anywhere from minutes, or typically minutes to hours. Those present a problem for the astronauts because they're considered radiation workers. They're up in space. We're protected here by our atmosphere and our magnetosphere, but they're kind of closer to the action, and that puts them at risk. And the primary hazard that they face when they're up there is an increased cancer risk based on that ionizing radiation. And then finally, you can get these huge eruptions, these coronal mass ejections that come off as well. There are images of the sun called coronagraph images. Those coronagraph images are key. We can use the coronagraph to see, for instance, a coronal mass ejection come off the sun. With the coronal mass ejection, you have a big tearing off of a blob of plasma that is explosively ejected from the sun. And we can say, okay, looks like it might be Earth-directed. This is when we have to prepare for geomagnetic storms. And we have, depending on the speed, from about 18 hours or so to 3 or 4 days. We see it in the coronagraph briefly, enough to get a handle on its speed. And then we don't see it anymore. And it's like a ghost moving through space. And it doesn't show up again until it hits a spacecraft that we have 1/100th of the distance from the Earth to the sun, and it hits that spacecraft, and that's the first time we actually understand what the magnetic field inside that cloud looks like. Those carry with them an embedded magnetic field. When they travel to Earth in hours to days, and they impact our magnetosphere, that can cause geomagnetic storming. Once it gets to Earth, so the magnetic field, if it's oriented correctly, sticks to Earth's magnetic field, starts ripping the field lines off as it passes over, and that violence leads to the fluctuating magnetic field and the geomagnetic storm. And then what's going on with the aurora, you've got particles that are injected into the poles. They interact with our atmosphere, and that interaction causes the glowing that you get from the aurora. And depending on the level of geomagnetic storming you have, it can push that aurora down to lower latitudes. In fact, in 1859, during the Carrington event, they got aurora down in places like Cuba, it was bright enough here in Colorado that miners got up to go to work thinking it was dawn, and really it was still nighttime. It can affect the ionosphere, so you can have communications problems. It can affect GPS, so you can have GPS issues. So those are some of the impacts we look for as well. Induced current on power lines, impacts to spacecraft, space station, risk to human health. Another thing that can occur is these energetic particles I mentioned earlier get trapped on our magnetic field lines and routed into the auroral regions. And that can wipe out communications over the poles for days. It's an event called D-region absorption. And when that happens, airlines have to reroute their flights to avoid that no communications area. And in doing so, burns up a lot of fuel. There's another type of feature that causes geomagnetic storming on a less severe level, and those are the coronal holes, these areas of the sun that are open, and they appear black, big dark regions. You can see them in X-rays and you can see them in extreme ultraviolet. And those regions have high-speed solar wind emanating from them. When they come around, they can give us some geomagnetic storming and pump up the electron levels. The different space weather effects that we see, and trying to ascertain what they came from, that's an important part of our job. Important part of the process is trying to determine, okay, we're seeing this particular impact on Earth. What can we ascribe that to? And generally, we can link, we have an understanding of, flare does this, particles do this, geomag storm does this, so we can see and look for those kind of impacts. So I think the way we tell where the impacts come from is by mapping it back to a particular phenomena that we observed, whether it was a flare or a particle event or a geomagnetic storm caused by a coronal mass ejection. So yeah, that's kind of how we go from impact back to origin. Usually we're working in the other direction though. We're observing an event and going forward to warn people that they could see impacts from an event. Operationally, we have to make decisions to send out warnings and alerts and watches before the graph is filled in. We get the line up to here, and we have to know or try to figure out what the rest of the graph's going to look like. What we're looking at here is a prototype of an electric field model, or E-field model, that will be able to depict in near real time the electric field over the continental US. This is important for power company operators because geomagnetic storms can induce current on power lines, and that induced current can in turn damage the transmission system, damage transformers if it becomes too large. This particular event we're looking at occurred in 1989, so this is a historical revisiting of the storm. And this storm caused a power outage in Quebec that spread down into the northeastern US. And it was significant in that it left a lot of people in the dark. As a meteorologist, I never really thought about the sun much other than, yep, it's in the sky. How hot is it going to make Earth today? Oh, it's where it's supposed to be setting in the evening. All right, we're good. That's about it, the level of thought that I gave to that particular thing. And it was amazing to learn how much was actually going on. And so we can walk around day to day, mostly not think of it, but when it does throw off something significant, it'll get your attention. And so that's what we're here to keep an eye on it. Differences between space weather and terrestrial forecasting boil down to a lack of observations in the space environment with the same density that we have in the terrestrial environment. We're swimming in data. In meteorological terms, it's kind of like you see a wave off the coast of Africa heading across the Atlantic, and you go, hey, that wave, that easterly wave might develop into something. Could be a hurricane. And then you don't get to see anything else until you get the phone call from Cuba, and the guy's like, ah! And it's kind of late now because it's in Cuba already. And that's kind of what it's like for us. If you think about the space era, we haven't been looking at the space environment with vehicles in space for a very long time. So this relatively short time scale, we haven't seen all the events that could happen. So it's kind of like if you think in terms of terrestrial meteorology, what's a 100-year flood, you know? And that's something that the scientists are now grappling with, beginning with the documentation we do have of events and kind of working through that and through the science to understand how bad a magnetic storm could be, how big could a flare be, and what would be the impacts then on the systems. The eclipse, I think the thing that'll be fun about that from my perspective is we're going to see, you know, we should be able to see what it does to the ionosphere, because that ionization, the UV and X-ray emissions from the sun that give us that ionosphere, you know, they're going to be turned off in this swath. So it would be interesting to see what kind of impact that has. You know, is it discernible? Is it something we can measure? Should people be worried about the space weather? I would say they should be aware of it. But if you think about it, how long have we been on Earth? A really long time. And you're not outside on a daily basis going, protons. Nobody does that, you know. You don't, it's not like hailstones, you know. In fact, most people don't even know it's happening most of the time. It's an amazing time to be a space weather forecaster and a scientist in this field. It's just absolutely amazing because we're learning more all the time, but there's still ways to go to hone our ability to forecast space weather, to get us to a place, you know, if we can get there, to a place where we're on par with what we can do currently with terrestrial weather. We're learning more. I think that the work that's being done in the research community and the recognition of the importance of the impacts of space weather and being prepared for space weather is all very encouraging. And I hope we can kind of continue that momentum. We need observatories in space and on the ground. We need research from the most basic understanding levels all the way through to the applied levels here. And part of our focus has been really trying to bridge that chasm sometimes between research and operations and weave these things together. That's an important thing, and it's awesome to be part of that. I mean, it's really an awesome job.
Thanks for that, Rob. It's fascinating to see how the different areas of solar physics play a big role in our understanding of the sun and how it affects the Earth. We really hope that you enjoyed our webcast this month and are starting to realise how all of these different pieces come together in the single field of solar physics. As we get ever closer to the total solar eclipse, it's a great time to get in touch with us with your questions. If you have any questions about content that we've already covered or anything that you would like to see us cover, please get in touch. You can email us at outreach@nso.edu. You can find us on Facebook at www.facebook.com/National Solar Observatory. On Twitter, our Twitter handle is @NatSolarObs, and on Instagram, we're @National Solar Observatory. Don't forget to subscribe so as you get notifications of upcoming webcasts, and we look forward to seeing you again next month.